SwayamPrabha. Digital India. Educated India.
In this lecture, let us continue and complete our discussion regarding the transport properties, followed by the governing equations of viscous high temperature flows. In the previous lecture, we were talking about transport of momentum, energy and mass as part of the viscous effects. We initiated a discussion regarding the relation between flow velocity and diffusion velocity due to species concentration gradients. We will complete that discussion and then we move on to high temperature transport properties of air, which is an extremely important issue when we handle hypersonic and hypervelocity flows. Then we move on to recapitulating the different forms of the Navier-Stokes equations, because in this week we are going to discuss about viscous flows, where Navier-Stokes equations is the backbone of the whole exercise, and the governing equations of high temperature chemically reacting viscous flow include the species transport equation, where diffusion effect has to be included. So, we will continue with those discussions in this week, in this lecture. You may recall that we discussed about superposition of bulk motion of the gas and the motion caused due to diffusion of species I in the gas mixture, and we realized that the flow velocity is essentially a sum total effect of the C I times V I of all the species of the gases in the mixture. And we said that different kinds of different kinds of concentration of the different species in the multi-component gas mixture may be existing, like the example that we cited over here of atomic and molecular oxygen. And based on how the mass fraction varies along the length of the device, you would see the diffusion velocities of different species varying. And finally, we talked about a result which you may try to work out later, that sigma rho I u I, where u I are the diffusion velocities of each one of the species is equal to 0. We discussed about thermal diffusion as well. We move on now to say that the mass diffusion of species I through a gas mixture can be driven by concentration gradients, temperature gradients as well as pressure gradients. In gas dynamics, however, the most dominating effect comes from the concentration gradients. The temperature gradient effects are much weaker and pressure gradient effects are negligibly small and therefore completely neglected. If we consider a viscous flow problem where conductive heat transfer and energy flux due to mass diffusion are dominant, neglecting the energy flux due to convection and radiation, then you can represent the q vector in this form, minus k into gradient of T plus sigma rho I u I into H I, where H I is the enthalpy of species I, where again the rho I into u I, this part can be represented in terms of the diffusion coefficient of the mixture and the gradient of C I. Let us consider a high temperature boundary layer kind of flow with gradient of T and gradient of mass fraction existing along the y direction. The energy flux in the y direction in that case can be expressed in this form, where you have only the temperature gradient along y accounting for the conduction, followed by the diffusion effect over here, which again involves only dCi dy in a partial derivative sense. Assuming chemical equilibrium and constant pressure along the y direction, we can show that the total conductivity is nothing but the thermal conductivity as well as an expression of this form, which is coming from the diffusion effect, and therefore, we say it is reaction conductivity with a subscript r associated with it. So, for the total we have a subscript capital T, while for the diffusion effect, which is essentially as a consequence of the chemical reactions which are going on, we have a subscript small r. The above concept of total conductivity is used to define an equilibrium Prandtl number, which has a subscript E q, where we make use of the k T expression that we just talked about in the previous expression, and of course, mu C p in the numerator for the Prandtl number. The k T and the equivalent Prandtl number are applicable only to flows where local chemical equilibrium exists and the energy flux is calculated in a direction along which pressure is constant. So, these are the constraints which have to be fulfilled in order to apply the concepts of k T and the equivalent Prandtl number. When we look at high temperature transport properties of air, these considerations are indeed met, and therefore, you will soon see the application of k T. Here we are looking at how the viscosity coefficient varies as a function of temperature with pressure as a parameter, where you have a reference value of mu, which is at standard conditions for non-reacting air given by the expression below with units gram per centimeter second, where T is of course the absolute temperature. Now, in the plot for mu by mu naught, which is essentially a scaled or normalized value of mu, which we are calling as the coefficient of viscosity ratio, you have temperature along the x axis in terms of thousands of Kelvin, starting from 2000 Kelvin and going up to about 14,000 Kelvin, and you see pressure as a parameter, as already mentioned, two different pressures, one is 10 atm, the other is 1/100th of an atm, and you can see the variation of mu by mu naught as a function of temperature. As you can see, up to a temperature of about 4000 Kelvin, the change is almost insignificant, and therefore, the ratio happens to be approximately 1, which is independent of the pressure. However, the mu by mu naught deviates from unity due to high temperature chemically reacting effect, and significant variations are noticed above 8000 Kelvin due to the effect of ionization. So, this is where we are talking about this, and beyond we are talking about significant changes. For example, at a low pressure there is a sudden dip in the value of mu, while at higher pressures, one order higher pressures compared to atmospheric pressure, we have about a 50% increase up to 12,000 Kelvin. Therefore, significant changes do occur because of the chemically reacting air and the ionization effects. If you look at the coefficient of thermal conductivity ratio, the k T, which comprises of k and k r, we see that along the x axis again, like in the previous plot, we have temperature represented in terms of 1000 Kelvin multiples, and along the y axis the k T by k naught ratio, where k naught is again a reference thermal conductivity, is almost 2 orders higher than the mu ratio that we saw in the previous plot, and significant variations are noticed for especially the low pressure ranges. The large variations are caused due to the effect of k r in this expression. This is because k r has a strong effect in chemically reacting air because of the significant role of diffusion when the air mixture starts reacting, and which is evidently going to be high at as the temperature gets higher, and you can see significant changes start occurring from 8000 or 10,000 Kelvin onwards. An interesting fact to note is that the equivalent Prandtl number has a more moderate variation than the kT that you see over here, because the temperature variation of kT and Cp, they practically cancel each other. Thus, in the temperature range of dissociation of air, the equivalent Prandtl number essentially remains between 0.6 and 0.8, which is a very moderate change with respect to the standard value of 0.7 that we use at lower temperatures. So, this is all about high temperature transport properties of air that we wanted to discuss at this point. And now, we move on to discussing about the governing equations of viscous flows, the compressible Navier-Stokes equations, and again we have to keep in mind that we are talking about high temperature reacting flow where viscous effects are going to be modeled. So, we start from the standard form, where as we can see over here, we have the continuity equation followed by momentum equation and finally, the energy equation mentioned using the index notation, which we learned much earlier in the course. Term by term, if you notice, the terms A and B are figuring in the continuity equation. The A term signifies the net rate of change of mass inside the control volume. The B term shows the net mass efflux through the control surface. So, one is a volume integral, the second is a surface integral. When you go to the momentum equation, you have 4 terms C, D, E and F. C stands for net rate of momentum change inside the control volume, which is again a volume integral. Net momentum efflux through the control surface, that is D, which is the surface integral. Net surface force, which is a surface integral, and net body force if we are accounting for them, again in the form of a volume integral. As is evident, this is one possible way of representing the compressible Navier-Stokes equation, where we are using an integral approach to represent them. Going to the energy equation, again we have 4 terms like the momentum equation. The first term G stands for net rate of energy change inside the control volume, which is a volume integral. The second term H is a net energy efflux through the control surface, a surface integral. The third one on the right hand side, work done by surface forces, which is a surface integral. And finally, the fourth term, the second on the right hand side, it is the work done by body forces as well as heat transfer. So, the heat transfer part comes here, the body force effect comes over here, and then we have an expression for sigma ij, which is equal to minus p times the Kronecker delta plus tau ij plus lambda kk delta kk del u kk by del x kk as the expression for sigma ij, where in the equation we had the tau ij term, which can be represented in a form like we have shown below. Again, the E term that shows up in the energy equation is represented here in the form of total energy, the internal as well as kinetic. To expand on the idea, we know that the different transport equations can be also written in their differential form, and if you write a form for the finite control volume Eulerian framework as we have shown on top, the corresponding form, which is of the differential kind, can be written like this at the bottom, and the connection comes from the Gauss divergence theorem. This essentially represents the Newton's second law in integral and differential forms, with the transport terms C, D, E, F mentioned once again. If you were to look at a similar approach for representing the energy equation, which is essentially the first law of thermodynamics, again by using the Gauss divergence theorem, you should be able to translate the integral form to the differential form that we see below. So, in this manner we should be able to recall all the possibilities that we had discussed earlier, which have been shown or put together in a single framework here. On the left we have the infinitesimal fluid element, which we can watch either from a fixed reference like the Eulerian framework, or follow the particle as in Lagrangian, or we can have a finite control volume. Again, we can either watch it from a fixed framework or follow the control volume, and the Gauss divergence theorem is able to help take us from the integral to the differential world or vice versa, as shown through those two arrows in blue and red. And the form that we have encircled over here is done with a purpose, where we are focusing at an infinitesimal fluid element observed from a Lagrangian framework, because we will spend a little more time on that particular form. It is not possible to proceed with all of the forms together, neither would it make much sense. So, we are just taking this encircled form forward, again keeping in mind that we are going to neglect the body force effects that we see over here and simplify them and write them in certain other slightly different forms as we take them forward. It is good time to recall the stress equation once again, which contains the normal components in the form of pressure followed by shear, and the bulk modulus, which is associated with the volumetric aspect. And therefore, as we recall, we can go ahead from a general form that we have represented over here to a form that we have shown over here for the respective components, where, as we may recall, that the lambda is the bulk viscosity coefficient, and we can write the forms for the different normal stress components. Here we find that we have included pressure in the normal stress components, but it is also possible to segregate the pressure out of the normal stresses and represent them separately as pressure gradient terms in the different components of the momentum equation. When it comes to mechanical pressure, it is the negative or the compressive stress, which is 1/3 or average of the sum of the normal stresses, and that is the average compressive stress on the fluid element, which is represented by the P bar expression over here. And then we see that it can be represented in terms of the thermodynamic pressure and the additional term over here, which according to Stokes' hypothesis is set to 0. And the difference between P and P mechanical can be expressed in terms of the bulk viscosity and the divergence of the velocity field. Having said that, we move on to putting all these knowledges together to write down the governing equations for chemically reacting viscous flow, the one that we are discussing here in the current perspective, and we choose to represent them in that encircled form, if you recall from the slide just a few slides behind. If you recall that form, then you will see that the global continuity equation, which applies for the mixture, can be written over here like this, because here we are not talking about a pure gas anymore, rather we are talking about a multi-component gas mixture in general. and therefore, on one hand we have to keep tracking the respective species. On the other hand, we are also going to look at the global effects, that means the mixture. Recall that originally our forms were like this. That was the form for continuity equation, that was the form for momentum. We already have mentioned that body forces would be neglected, and now we are kind of getting used to different nomenclatures, different forms of the conservation equations, so that we can handle them more flexibly. Coming to the x momentum equation, we represent it in a form where pressure has been segregated out, as already mentioned that you can do that by taking it out from the normal stress components. We are representing the different stress terms, whether they are normal or shear in general, in a form like tau ij, which is a slight difference to what we showed a few slides back. That is where the adaptation to different nomenclatures becomes important. And then you realize that all the tau ij terms that we see in the x momentum, y momentum and z momentum equations above, they can be represented in a general form like this, where tau ij and tau ji are identical, and they are represented in this form: mu times del ui del xj plus del uj del xi, and from there graphs these three expressions for tau xy, tau yz and tau zx. Similarly, you have an expression for tau ii, where it is of this form: 2 mu del ui del xi, not in the sense of a summation though. It is going to be represented in a form like this, where you have 2 mu del u del x, then 2 mu del v del y, 2 mu del w del z, and summed with lambda times divergence of v. Coming to the energy equation, we have the original form like this, where we are neglecting the body force, and with the current nomenclature we can express it in a form like this. The energy equation shows that the change in total energy, which is E plus V square by 2 of a fluid element moving along a streamline, would be affected by different effects. First of all, due to thermal conduction across the fluid element surface. Secondly, energy transport by diffusion into or out of the fluid element through its surface. Then comes the possibility of emission or absorption of energy due to radiation. Rate of work done by pressure forces exerted on the element surface, and the rate of work done by shear and normal stresses exerted on the fluid element surface. So, all these effects actually figure in an equation like this over here, where the effects become more appropriately visible when we define the heat flux vector, the q vector over here, in terms of its components, which includes conduction, diffusion and radiation effects. The conductive effect shown here, the diffusion here and the radiative effect over here. The diffusion term, as you can see, includes effect of all the species in the gas mixture, the way they affect the energy transport that has been modeled through the summation. K is the mixture value for thermal conductivity, which can be calculated using the approach discussed earlier. If you recall, in the previous lecture we had discussed about how to calculate the mixture value. Now, the equilibrium thermodynamic properties for viscous chemically reacting flow in local chemical equilibrium can be given in the form like we have shown over here: pressure expressed in the form of function of internal energy and density. You can pick up two other thermodynamic properties too in order to express pressure as well as temperature. For chemical non-equilibrium flows, we derived the species continuity equation, but that was done in the context of an inviscid flow, and there we had used a fixed finite control volume like the one that you see over here, where rho I was the mass of species I per unit volume of the mixture. Summing rho I gave us the mixture density, and then we considered the effect of the mass of species I inside the control volume through the volumetric integral rho I times dV, the net mass flow of species I out of the control volume through this surface integral rho I v dot ds, and we defined rho W I dot as the local rate of change of rho I as a result of chemical reactions inside the control volume. Hence, we notice that the net rate of change of the mass of species I inside the control volume would be caused due to net flux of species I through the control volume surface and the creation or extinction of species I inside the control volume. All the effects put together would give rise to the species continuity equation, which is given in integral form here. However, we again need to recall that that was done for inviscid flow, and we now need to figure out how it will vary for viscous flow. Just to carry ahead with the discussion that we had in the context of inviscid flow, we recall that the differential form of the species continuity equation for a given species I was further written in terms of an expression like this: mi, the molecular weight, followed by di dt, and the di dt, a detailed expression of the chemical reaction model was written in order to obtain this. And for a non-equilibrium chemically reacting mixture of high temperature air with n different species, we would have n such species continuity equations typically. For each such species continuity equation, we would have to include all the relevant chemical reaction equations, which we have indicated over here, the chemical reaction model, and write the corresponding n rate equations for the right hand side term. So, this is basically the rate equation that we are talking about, since it is a non-equilibrium. Finally, if you recall, we would utilize only n minus 1 of those species continuity equations, while one of them will be replaced by imposing the constraint equation for mixture density, where the sum of species partial densities equation will be deployed. And some alternative forms of the species continuity equation was also derived and studied at that time. So, starting from this equation, we showed that the equation can be further expressed in a form like this, where a part of those terms would go to 0 for the sake of implementing the constraint of global continuity equation, and therefore, it would reduce to a form like this, which is involving the substantial derivative, and therefore, that represents the time rate of change of the mass fraction or the mole mass ratio as we follow a fluid element along the flow. And in terms of the mass fraction and the mole mass ratio, the equations would figure in these two forms respectively. As we said earlier, that was the part coming from inviscid equations. We have now got to address the question that how is this derivation of species continuity equation going to be affected for viscous flow problems. We have already learnt about mass diffusion due to concentration gradients in viscous flow. Therefore, mass transport of species I has to be included in the species continuity equation. Now, for an inviscid flow, the velocity v, which we have shown on the control surface, is applicable for all species in the gas mixture. This is because there is no mass diffusion effect. All the species I move with the same velocity, and that is namely the mixture velocity v. Therefore, v stands both for the mixture velocity as well as the velocity of all the species. However, as we know that for viscous flows they are distinct. In fact, we then have an equation which looks like this for each species separately. Hence, through the control volume, if we consider only the flow of species I rather than the mixture, then the velocity v must be replaced by v I, and then the species continuity equation essentially becomes of the same form as the overall flow that we had derived for inviscid flow. So, this equation is derived based on the same logic as the pure gas species equation in inviscid flow, or even a gas mixture in inviscid flow, where all species would essentially behave identically in a kinematic sense. From the above integral form, we obtain the differential form that we can show over here, and remember that the V I that we have over here is now going to be of a form like this. Therefore, the differential form finally gets written here, where the V vector is essentially the mixture velocity, while the U I vector is essentially the diffusion velocity for a particular species. With a little bit of calculations, we can actually show that rho times the substantial derivative of C I is divergence of rho I U I, which is this encircled term, equals W I dot. And therefore, if you compare with the inviscid form, where it was d C I dt is equal to W I dot by rho, then you find that only this term makes the difference. By the way, this equation can be obtained by replacing the rho I over here in this equation by C I times rho, and then using the global continuity equation, with which you should be able to derive this form. And now we are talking about comparing this form, which holds for viscous, with the form that we have already learnt, which came from the inviscid domain. And the difference between the two is essentially the additional term involving diffusion velocity, which we have already taken note of. And then that diffusion velocity term can be further replaced in a form like this by using the Fick's law. And therefore, this would be the form we would be interested in if we involve the substantial derivative of C I. For a non-equilibrium viscous chemically reacting flow, the governing conservation equations that comprise of global continuity equation, the three components of momentum equation, energy equation, the heat flux vector, and one of the forms of species continuity equation as we discussed above, have to be simultaneously solved or implemented. Again, if there are n chemical species, then n minus 1 species continuity equations, along with the relation sigma C I equal to 0, sigma C I equal to 1, I am sorry, are solved. Additionally, we have the equation for E, which is sigma E I times C I, and for diatomic molecules, the E I expression will be of this form. If local thermodynamic equilibrium is assumed, then the vibrational energy of the species I would be given in this form, while if local thermodynamic non-equilibrium exists, then we have to have the vibrational rate equation with the effect of the diffusion velocity incorporated. Let us conclude by saying that in this lecture we discussed about the relation between flow velocity and diffusion velocity due to species concentration gradients. We discussed about the high temperature transport properties of air. The Navier-Stokes equations are applicable to high temperature chemically reacting viscous flow and their form was discussed. The species transport equation was modified with respect to inviscid flow to account for the effect of diffusion velocity. Thank you.